Hey, what's going on, guys? CodeMikeGains here. In this video we're going to implement the function that will return us the index of the least significant first bit of a current given bitboard we're supposed to be sending as an argument to this function. But before we start, let me actually show you a bit hack and share the idea and the concept this function is going to be based on. So let's scroll down to the very bottom of our source code, and I don't really want to print this count bits anymore, and well, let's actually first try to open the terminal in the current working directory by typing make debug, and if it makes, I want to run the BBC binary executable here. Okay, hold on a second, it just runs the previous version, so here it is. So here's the least significant first bit we need to get an index for. So by saying get an index, I mean that if we will use that index in order to set a bit on a current given index, we'll have the bit been set at exactly the same place where it is kind of available right now, and I will demonstrate this to you later on, just right in a moment. So first let me show the bit hack. So print bitboard. And the idea is very simple. If we simply say like, so I would be using this block bitboard as an example. So if I say block bitwise ended with minus block, then in return we will get the least significant first bit being isolated from all the other bits. So here it is. And now the very last thing left here is actually to convert these zeros to ones and pass the resultant bitboard to the count bits function in order to actually count this trailing ones, and the number of trailing ones would be the exact number of would represent the index of this least significant first bit. So in order to make that little trick, we need to enclose this expression within the parentheses and subtract 1. So now we have this trailing zeros being converted to the trailing ones, basically. So now, based on this simple hack, we can already go for implementing our get less significant first bit index function here. So let's go to the bit manipulations, and just right below this count bits, we'll create a function to get least, let me just grab this from here to save you time from watching me type in this, get least significant first bit index, and this would be static inline int, just like count bits, due to the reason of this function being heavily used within the mode generator. So just to make it faster, I'm using the static inline keywords here. So, and let's call this get less significant first bit index, and it would take U64 unsigned lolon, also known as a bitboard data type called bitboard. And the very one of the very important restrictions regarding this method, we need to make sure that the bitboard we're passing into this sort of a function is not equal to 0. So we need to make sure bitboard is not 0. And in order to do this, we can simply say if bitboard and otherwise else, we just want to return illegal index. So simply say return -1 like this. Okay, and here we just need to count trailing bits before a least significant first bit. So I hope it's quite pretty clear that this LS1B stands for least significant first bit. And here we can simply return our count bits function, and our expression that I've been introducing to you guys. So we take our bitboard, bitwise ended with minus bitboard and -1, and we're done basically. So now let's try to call this function right over in here. So just printf and index, and this would be the decimal number, and we want to say get less significant first bit index for our block bitboard. So I would be using this one. Okay, block, save, and let's run this. So it gives us an index of 11, and now just to make sure that this index is actually correct, I will create a new test bitboard, and I will set a bit at the index of 11, and the bit would appear right over in here. So let me just create a test bitboard here. So test bitboard u64 test equals to 0 ULL, and now we just want to set bit and this test bitboard and the value taken from the result of this function, and eventually I want to print the bitboard test like this. So we have a bit been set up accordingly right over in here. But very last thing to consider here is that you actually need to that it's not really that you know, like it's not that comfortable to get these indices as integers. So it would be much better to convert these indices into human readable coordinates, and like E2, E4, and so on. And remember, some videos ago we did create this sort of, it's not a data type, even not a data structure, just a commanded part, and now we'll finally start making use of this sort of a stuff. So I want to create a variable called, so this would be the constant character, and we call this square to coordinates, okay, and like this. And also it should be character pointer, because we're pointing to the strings. So I really hope the definition is correct. Yeah, it seems like. And now we can make use of this sort of a coordinates the following way. So it would just now simply trying to print, so print, or we can even do this right over in here. So let's say coordinate, and this would be the string already, and here we can reference our square to coordinates array, and indexed by the return value of our get least significant first bit function. Okay, so let's try to print this one more time, and we get this coordinate of D7 right over in here, so which is absolutely what we kind of need here. So it's not really that clear that index of 11, where is this, but the coordinate of D7 is a much clearer way of representing things. Also, we'll be making a huge heavy use of this square to coordinates array later on when we would be generating our moves, and this also would be needed for the UCI protocol purposes to print the best move that engine has found. So just just to follow those UCI protocol guidelines and formatings regarding the algebraic notation for moves returned by your chess engine. Well guys, so this is it for this video, and I hope you enjoyed it and learned something interesting out of it as well. So from now on, we're almost there at the point where we would be actually initializing our attack tables for sliding pieces, but we'll need one more function to implement before that, and that function is called set occupancy, and this would be covered in the next video basically. So make sure to follow the series if you don't want to miss it, and starting from the next video it should get more interesting. But obviously, you know, like, I personally believe that when you've already once created a chess engine with, say, array-based board representation, you're not in a hurry anymore, so no rush to trying to create the chess engine as soon as possible. But instead, I feel like I can enjoy the process of both making these videos and actually developing the chess engine that is going a couple of steps further compared to this series. So obviously, first I'm writing this, and then I'm making that. Then I'm covering everything that I've already written within this video series. So thanks for watching, guys. Thanks for your attention. I really appreciate that. Until the next time, and take care.